question 5 introduces the idea of atom economy, which is a different way of looking at the efficiency of a chemical reaction. And basically, to get a proper overview of how efficient and therefore how sustainable a process is, you need to take in account of both, because they're not sort of alternatives, they're both aspects, different aspects of the same thing. So the idea is that the percentage yield tells you about how different the real world is from what the equation said you would get. So it takes account of the imperfections that happen in a reaction. What atom economy does is to say, well, even if things happened exactly as it says they would in the equation, a process can still be wasteful. So, for example, if we think about ways of making that compound, you could make it from ethene by reacting with you can make it from ethane by reacting with bromine in the presence of UV light, and you can make it from ethene again by reaction, this time with hydrogen bromide. And you might think, well, if I had 100% yield, then those are equally good. But actually they're not, because if you think about the actual equations for this one, you have C2H6 plus Br2 goes to the product plus HBr, whereas for this one we just have C2H4 plus HBr goes to that product only. And the point is that the HBr is likely to be a waste product. That's not a sort of chemical that has a massive use in the everyday world. So the chances are that would be a waste product. Whereas you can see in this process there is no other product, so there is no waste product. And that's what atom economy tries to get to grips with. So what it measures effectively is what percentage of the mass of materials going in actually ends up as a useful product. And you could see that for this reaction, which is an addition reaction, the answer is 100%. If it goes as the equation says, 100% of the mass that you put in will end up as the right product. Now, of course, that probably won't be exactly true, because there will be a percentage yield that's less than 100. But as I say, we're not thinking about that here. We're thinking about what does the equation tell us, and it tells us this one is not wasteful at all, but this one is, because HBr, is probably going to end up being chucked away. So the way you calculate atom economy is by following this definition. So atom economy is the MR of the useful product or products, but in our calculations we'll usually just focus on one, so we'll say it's the MR of the useful product divided by the sum of the MR of all products, and then times 100 to turn it into a percentage. It looks like a weird definition, but as I say, what that gives you in practice is what fraction of the mass of materials you put into the reaction mixture end up as the useful product you're trying to make. And you can see how that is a sensible number to calculate. When you use this definition, it's important to realise that these numbers are weighted by the numbers in the equation. So, if you have, x plus y goes to, 2q plus 3p, then your atom economy would be equal to 2 times, for, then your atom economy if Q is your desired product, your atom economy would be equal to 2 times the MR of Q divided by 2 times the MR of Q plus 3 times the MR of P, all times 100. Okay, so you've got to be careful of that when you put it in words there, because it doesn't say it explicitly, but you've got to include the balancing numbers like that when you work out the atom economy. Okay, so we can put that idea into effect then in question 5. So this is a reaction which is used industrially to make tetrafluoroethene, which is the monomer for making Teflon, which is the sort of non-stick polymer. So it's quite an important process, and we can calculate how efficient it is, because obviously the concern is that it's producing HF as well. So HF has some uses industrially, but again depends on the setup. It may end up going to waste. So we plug it into the definition. Atom economy is the MR of the useful products divided by the sum of the MR of all products times 100. Okay, so we're producing just 1 mole of that, so it's just the MR of C2F4, which turns out to be exactly 100 on the top line, and then on the bottom line it's the sum of the MR of all the products, so there's the 100 again, but then there are 2 lots of HF, so each HF has an MR of 20, so plus 2 lots of 20. Okay, so that's the very important thing, that you've got to include that factor in the equation there. So that's times 100. So that's going to be 100 over 140 times 100, which is 71.4%. Okay, so what that's saying is that even if this reaction goes brilliantly and you don't get any wastage, so you don't get any different products being formed, you don't get any of this left unreacted, you don't lose any of it while you're trying to purify stuff, even in that perfect world, you're still going to waste more than 1/4 of the mass of this going in, because it ends up as a product that you're not using. And that's why atom economy is important to take into account, because it stands there alongside percentage yield as sort of twin aspects of how sustainable a process is going to be. So then we turn to the other side of the coin, which is the percentage yield, which says, well, actually this reaction isn't perfect, that actually not all of that ends up as these products, at least not in recoverable form, and we're told that the percentage yield is actually only 84%. So then we can calculate how much of this we'd get from a given starting mass of trifluoromethane. So the first job is to recognise that we're told that we have 1 tonne, which is 1 times 10 to the 6 grams. Remember, it tells you on your data sheet that 1 tonne is 10 to the 6 grams, so that's not necessarily a number you have to remember. So that's the mass. So we can turn that into moles, which is mass over MR, is 1 times 10 to the 6. And if you add up the MR of that, it comes to 70.0. And that comes to 14286 moles. So then we come to the theoretical yield, and you can see that the equation says that 2 moles of that just give you 1 mole of C2F4. So that means that the theoretical yield of C2F4 is just going to be half this number of moles, because this says however many moles of CHF3 you've got, you should, according to the equation, get half as many moles of C2F4. So half of that number, which is 7143 moles, is the theoretical yield of C2F4. But now we want to find out what the actual yield is. So you can approach that really in two ways. It may be sort of obvious to you that if the percentage yield is 84%, the answer is just 84% of that, and that's fine. If you're not comfortable with that, you can approach it by rearranging the expression. Okay, percentage yield is actual moles over theoretical moles. Times 100, which means that the actual moles are equal to the percentage yield times the theoretical moles divided by 100, which is a different way of arriving at the same thing, because you can see multiplying by the percentage and dividing by 100 is the same as just finding 84% of that. So it doesn't matter how you approach it, so long as you're comfortable and confident with the way you're doing it. You know, this is the sort of, I suppose in a way, the brute force approach, but it's also the safest, because you just think, well, I'm just rearranging equations like I always do, and that's a safe thing to do then. So that's going to be 84% times the theoretical moles is 7143, divided by 100 gives you 6,000 moles. Okay, so that's the actual moles that would be produced. So it's 84% of what we theoretically reckoned we could get. And so we just then have to turn that back into a mass. So the actual mass obtained is moles times MR, which is 6,000 times 100, because the MR for C2F4 it just happens to be exactly 100, which is 600,000 grams. And that would be fine. You could leave the answer as that, but if it wanted it in tons, you then just have to divide by 10 to the power 6, which gives you 0.600 tons, if you wanted to turn it back into that. So then in part 3, it's saying, well, what about the actual polymerization reaction? So we've made our tetrafluoroethene, which is this. And the reason we've made it is so that we can polymerize it to make polytetrafluoroethene, which is what people commonly call Teflon. So what about that reaction? So remember, for polymerization equations, we can't specify exactly how many react, so we use n to represent a big number. So a big number of those get together, and remember, the way to formulate these equations is that each monomer becomes a repeat unit, and the structure of a repeat unit is always that those two carbons that were the doubly bonded ones are now a singly bonded pair. The double bond is broken, and instead you have these two linker bonds on the end which connect one repeat unit to the next, on this side and also on that side. The four things at the corners, the four fluorines in this case, are still there, so you just put those on the corresponding bonds like that. And then the key thing to remember is that if you put a bracket around it so that it slices through the linker bonds at the end, so you've got to draw that carefully to make sure it slices right through those bonds. And then you can say, right, what the polymer is that basic unit repeated n times to make a long chain. So you put the little n down there, and that's your equation for the reaction. And then in part 4 it asks us to calculate the atom economy for that. And there's no need to break your calculator out for this one, because of course this is the only product of the reaction. So the MR of this divided by the MR of all of the products is just the MR of this divided by the MR of this, which is 1. And 1 times 100 is 100. So in other words, the atom economy is 100%. And that will always be true for any addition reaction. Okay, because in an addition reaction you only get one product. And so people who are working on trying to improve the sustainability of chemical processes are always on the lookout for addition reactions, because they are the best news in terms of minimizing wastage. So any addition reaction, atom economy 100%. In part 5 now it's asking about the reaction of this compound tetrafluoroethene with hydrogen. So this is one of the standard addition reactions of alkenes which you should know about. So the equation for that say it's an addition reaction like all these alkene reactions. So all that happens is that the atoms that are already there stay there. So the C2F4 are all still in place, but the double bond is gone, and instead you add across it the H and the H from the H2, so you get that as your product. And it asks for conditions for that, and the answer is that you need a nickel catalyst for that reaction. Atom economy, well, again, as we've already said, if there is only one product, then the MR of that divided by the sum of the MR of the sum of the MR of all of the products is just 1. So the atom economy is 100%, as for any addition reaction. Part 6 is talking about what happens if you change the amount of the catalyst used in the reaction mixture, and how does that affect the atom economy and the percentage yield. So you can see that it doesn't change the atom economy because that's just a function of this equation, and the catalyst doesn't change what the reaction is, it just makes it happen faster. Okay, so the catalyst speeds up the reaction, but it doesn't change the outcome, and therefore the atom economy will still be governed just by that equation. Now the percentage yield is a bit trickier, because it depends what the reasons are why the percentage yield isn't 100%. If you have competing reactions, so in other words, if the percentage yield was only 80% because some of the molecules reacted to make a different product than the one you wanted, then actually a catalyst could change the percentage yield there, because if it speeds up the process you do want at the expense of ones you don't, then you could improve the percentage yield. So the question really is kind of wrong. I think the percentage yield could be affected by the catalyst, but if it changes the rate of the reaction that you want to happen relative to the rate of the reactions that you don't want to happen. So I don't really necessarily agree with my own question there. I think certainly it's true that the atom economy is what it is, it's just governed by the equation, but the percentage yield could be altered by the catalyst. Okay, so in question 6, we're taking 1-methyl cyclohexane 1-ol. So there's the cyclohexane. Cyclohexane 1-ol means you have an OH attached at one of the positions in the ring, and if it's 1-methyl, it means that same carbon also has a methyl group attached. So that is 1-methyl cyclohexane 1-ol, and it's reacting with HCl, and that produces a substitution reaction. We normally learn this reaction as a reaction with sodium chloride and concentrated sulfuric acid, because that's the normal way of generating the conc HCl and giving you a faster rate of reaction because it's acid catalyzed. But HCl will do the same thing. So if you weren't familiar with that reaction, it's just a different way of doing the reaction that you're familiar with sodium chloride and conc sulfuric acid. So it gives you that plus water as your other product. So that's your reaction equation. And the type of reaction is obviously substitution, because OH is lost and Cl goes in its place. So that's a substitution reaction. So then we have to calculate the atom economy and the percentage yield. So if we do the atom economy first, okay, so always write down the definition. So it's the MR of the useful product divided by the sum of the MR of all products times 100. So the MR of this is 132.5. so we can plug that into here and get that the atom economy is 132.5, because that's the useful product, divided by 132.5 plus 18 for the water times 100, which works out as 88.0%. Okay, so that's not too bad, but it does mean that 12% of the mass of the stuff you're putting into the reaction doesn't end up as useful product. It ends up as water, which of course is just going to get chucked away. At least it's not a dangerous product, so it's not difficult to dispose of, but nevertheless that's to an extent a waste of the resources that you were putting in. So turning then to the percentage yield, the information we're given is that we start with half a gram of this and we end up with 0.55 grams of that. So the mass of the product is actually bigger than the mass of the starting material, but of course that's not what counts, it's the moles that matter. That's what's affecting our percentage yield, because that extra mass comes from introducing the chlorine, not from any magic that we've brought about. So, as always, what you need to do is to turn these masses into moles. So we get moles of that is mass over mR, which is 0.50 divided by the mR of that compound, which is 114, and that comes to 0.00439 moles of our starting material, and that will be equal to the theoretical yield, because you can see from the equation that however many moles of this you start off with, theoretically you get that same number of moles of product, because one of these goes to one of those. So that's equal to the theoretical yield. And then we can work out the actual yield. So the moles of this, again, is mass over mR, which is 0.55 divided by 132.5, which is the mR of that product, and that comes to 0.00415 moles. So you can see that once we convert to moles, the moles of product is less, albeit not that much less, than the moles of starting material. So that makes sense, because there's going to be some loss somewhere along the way. So then we've got all the information we need, because that's our actual yield, and so we can plug those numbers then into our percentage yield expression. So always write it down. As with everything else, don't just put the numbers down. So percentage yield is actual moles over theoretical moles times 100, which is 0.00415 over 0.00439 times 100, which is 94.5%. Okay, so quite a respectable percentage yield in that case.